there, faithful geometry students. I'm just making this helps video for assignment 56. A couple of you have asked some good questions. Thank you for asking and keeping them coming. I'm going to go through a few of the things that you have asked about. So here we go. First one was question number 24, and the question was asking what happens to the overall surface area and volume if you multiply by a factor of x. So what we need to keep in mind here is what you're actually doing is you're taking this x value and you're putting it in here with the r value. So you have xr, and that's the part that gets squared then. So we still have our 4 and our pi and our xr squared. So when you go ahead and do that, what you end up with is 4 pi with an x squared and an r squared, because both of those things get squared. And what that looks like now, you still have your 4 pi r squared, but it's also multiplied times the x squared. So what that really means is that the whole surface area is multiplied by x squared. Okay, so you have the original and it's multiplied by x squared when you multiply this part by a factor of x. Similarly, if we multiply this by a factor of x, we have xr again, and instead of being squared, it gets cubed. So what you can see happening here for the volume is that since both of these things are cubed, if we did something similarly, that your volume would be multiplied by x cubed, because it's right there in the cubed spot. So that's what they were really asking for, that question. Now the purpose of these type of questions is so that you can have an idea of what's going to happen overall to one value as a result of another value increasing. And so this is kind of an open-ended type of a thing. This might be something where if they're trying to see how well you think, they could possibly put in a new scenario, not necessarily with this formula, in the SATs. And in SATs, they're trying to figure out how well you can take a concept and expand on it. So that might be helpful to you in that. All right, number 27, someone asked, could I please draw it out? Because this one was asking if you had some kind of a spherical something that you needed to paint. All right, how much paint would be needed? So they told you that you had a sphere with a radius of 30 feet and asked you how many gallons it would take to cover it. So this is really just a hidden surface area problem. So you need to find the surface area of this. So you'd plug in your numbers. You'd use a calculator to do 4 times pi times 900. When you did that, you'd have an answer. That would tell you how many square feet is in the surface area. But then you'd have to use this idea that they tell you that 1 gallon will cover 150 square feet. So that means you'd have to divide the number you got by 150, because each gallon is going to cover the 150. It gives us 75.4 gallons, and I believe that that's the answer that they put in the back of the book. But in practical sense, because we want to make this as useful to you in real life as possible, in practical talk, you're not going to go to the store and say, can I please have 75.4 gallons of paint? You have to buy it by the full gallon, so you would have to go and buy 76 gallons. And you're thinking, wait a minute, that doesn't follow the rules of rounding. No, it doesn't follow the rules of rounding. But if you only buy 75 gallons, somewhere you're going to have a blank spot in your surface. So you have to always, when you're talking about buying something, and you have to buy it in entire whole increments, you have to suspend the rules of rounding and always round up in those instances. So just kind of keep that in mind. You're doing your math, but you're also keeping your thinking going so that you're not taking yourself short. That's the thing about geometry, is you have to always be thinking about the context of the question. What am I using this for? And then your geometry helps you figure things out, but then your common sense has to say, wait a minute, I can't buy part of a gallon of paint. I can't tell them I want 75.4 gallons, and that might even be a rounded value, so you'd be just a little bit short. So you've got to use common sense in that. Okay, now another one dealt with a racquetball, and so if you don't really know what a racquetball is like, you may not realize that a racquetball is hollow in the middle, which is different than a baseball. A baseball has a solid core in the middle, which is different than other things. So a racquetball is more like a basketball or a soccer ball that's hollow in the middle, but they're made completely of rubber. And so the way it is, you've got this rubber outside and you've got this hollow inside. I'm not sure exactly how they're made. You could look that up if you wanted to. But what they're asking for is they're asking for how much rubber it would take to make this part of this ball. Okay, you don't need to have the core. The core is hollow, so nothing in there. So the way that you would do that, consider this as being a sphere, like a ball, and there's a hollow middle in it. So to find out how much is in here, you take the volume of the outside part and then subtract out the volume of the inside part. So over here, it said that the diameter was 5 centimeters to the outside of the ball. So that means that the radius is only half of that, which is 2.5 centimeters. And we use our formula, 4/3 pi times r cubed. That'll give us the volume of the outside. The inside, which is hollow, you're using 4/3 pi times this inner radius that they gave us, 2.25 centimeters. And when you do that math, you have about this much. So you take your outside part and you subtract your inside part, and it tells you how much rubber is just in this part right here, which would be your ball. So you'd have 17.7 cubic centimeters to make that ball. So that's another thing where if someone were manufacturing, they would need to take into account how much materials are needed for that. Okay, you can even do things like well, there's all kinds of things. Like I've seen like crunchy chocolate bowls at some point, I seem to recall, where you have like a coating of chocolate on top of a balloon or something. I know I saw that somewhere. And so if you wanted to find out how much chocolate you would need for your coating on a chocolate ball, that would be something else like that. Sorry, I'm in a food type of a mood today. So anyway, so we have that. The other question that was asked was a review question that goes back to some other thinking it through type of things. And this again, I'm glad that the person asked this because it can really tie into what happens in SAT type questions where they're asking you to think of something new. The question was, if ST is half of SV, then T is the midpoint of SV. They asked if that's true always, sometimes, or never. So they don't tell you where V is located. So one of the possibilities is you could have another V, and V could be out here somewhere. And so in this case, if it is twice as long, if SV was twice as long as ST is half, okay. All right, so in this case, T is not the midpoint. Okay, so you know that it's not always going to be true, but is it sometimes true? Well, sure, you could have V out here somewhere so that ST was half of SV. So it might be true, but it might not be true. So your answer to this question would be sometimes. Okay, so sometimes that would be true. So I'm glad you asked. And we have that. I'm going to also, somebody also asked, could we talk a little bit more about that latitude and longitude? So I want to bring it into possibly some things for you to understand. Somebody had said that they didn't understand about the degrees and where the latitude degrees came from as far as being from 0 to 90. So let me address that question really quickly. So we're thinking about a sphere here, and we have our latitude lines that are going around like this. So let me just quickly sketch in. So you've got your latitude lines. The latitude ones are that go sideways. So we're thinking about, these things. We've got the equator down here. Okay, here's our equator, just really quickly drawing it out to kind of make it 3D-ish. So we've got our equator down here. And so our latitude lines, the ones that are increasingly small circles, they said they didn't understand where the angles have to be somewhere between 0 and 90 degrees. Well, if we think about the center of our sphere, and this comes out here, and so our number of degrees for that comes from this angle, this central angle that goes from the equator, which is 0 degrees, up to however many degrees this might be. This looks like it might be about 35 degrees. So the 35 degrees, because it's a sphere, comes out to all these different spots along this circle. So 35 degrees north latitude would be the same level all the way around the globe. Okay, now why is it from 0 to 90? Because when you get to the North Pole, that's where 90 degrees would live. Okay? But then when you come down over on this side, if you tried to go past 90, well, it's going to be on the same circle. Okay, it's going to be on the same circle that's going around the top up here. So its number of degrees would come from this. Okay, so this might be 80 degrees. And so if this is 80 degrees over here, it would be 80 degrees over here as well. Okay, so we're going to continue this out so that if you had it flattened out on a flat map, okay, so we've got our latitude lines going this way, and we've got our longitude lines going this way. Okay, so let's say we have our 0 degrees here. That would make this north up here, and this would be south. And if we had, let's say this is our prime meridian, so 0 degrees this way, and so you would have, let me just make this simple here. Let's make this 15 degrees, and let's make this 30 degrees. We'll make this 35 degrees, and we'll make this one, looks like 20 degrees. I didn't do them very evenly, but that leaves me room for doing this. And let's make this one 30 degrees, and make this 60 degrees this way, and 30 degrees this way, and 60 degrees this way, keeping in mind that this is north and this is south and this is west and this is east, because that's how we do them. And so if you had, let me put a whole bunch of spots on here just so you kind of know what you're going to be dealing with. So if I had some cities here, city A and city B, city C, city D, city E, and city F. Okay, and we asked which city is, I need more space. Let's go this way. Here we go. Which is at, let's do 30 degrees east longitude and 20 degrees south latitude. Okay, 30 degrees east longitude and 20 degrees south latitude. So that would be the longitude, remember, this way. So we look for 30 degrees east. And then we look at 20 degrees south, because north is this way, south is this way, and that would be city C. I'll make this a little darker. And if we looked for what is at 30 degrees west longitude, and 30 degrees north latitude. Okay, longitude this way, so I'm looking for 30 west, and I'm looking for 30 north. Here's the north one, and that would be city F. Okay, so you would be able to do something like this, but just to answer the question that somebody asked, where those lines come from is how far it is from the equator if we're considering the lines that go to the center. But this question is more practical for the quiz that you're going to be working on. So there we go. I have answered you, and I hope that that makes sense. And I will be looking again for your questions to number 57 and trying to get something out there before you do your quiz to tomorrow. All right, God bless.